Hello kids, this is unit 9 for grade 7 science, which was about magnetism, right? So let's get on with this unit, right? What is magnetism? Magnets are materials which have the ability to pull other metals, right? Now, not all metals, not all metals are magnetic, right? We've got few examples, right? And what are the magnetic materials? We've got iron, right? We've got other metals. We've got neodymium, right? Neodymium. We've got cobalt. So there are many metals, few metals which are magnetic in nature, right? And iron is most common. So what is a magnet, right? Magnet is an object that has the ability to pull other magnetic metals, right? And we had seen this image. We did this experiment, with the iron powder in the lab. What is a magnetic field, right? So magnetic field is the area around which the magnetic effect can be felt, right? This area where you can see that the magnet is able to pull these particles to itself, this is what we call as the magnetic field. Now this is very large, the image is very small. You can see that the particles are aligned all over the place. So this area where the effect of the magnet can be felt or observed is what we call as a magnetic field, right? Now, to identify magnetic field, we use the compass, right? If you remember the compass. Now, remember this pointy part is the north of the compass. Keep that in mind. That this is the north, right? And this part is the south. Now, if you remember, opposite poles attract each other. So, if I were to place a compass closer to a magnet, it will always point towards the south of the magnet, right? So it will always be opposite in nature, right? So if the compass is pointing north this way, then imagine that the south pole is on that side. Now this goes same for the earth. Now if you take out your compass in your phone, if it is pointing north this way, right? Then imagine that's where the southern pole is, right? Of geological, right? Geological southern pole. That means the Earth's southern pole is going to be where the north of the compass is pointing, right? And what is a compass? Compass is a device which has a floating magnet, small little floating magnet which can rotate, and it gives you the direction of any magnetic field, right? You remember we did this magnetic line tracing, right? We called it line tracing, right? This magnetic line tracing is a method where you can identify where the magnetic field is of an unknown magnet. Obviously, when there's the north and the south marked, you can easily draw these lines, right? In the assessment there was a question where you had to draw these lines. So remember, if the question states draw magnetic lines, you have to start from north and they must end on south. So remember, these arrows represent the direction of the magnetic field, right? So don't forget to draw these. So remember, the magnetic field always starts from north and ends on south, right? That's how the magnets or the compasses work. Now, this is a basic idea of how the magnetic attraction or repulsion works. So opposite poles, uh, they attract, right? And same poles, whether they're south-south or north-north, they will repel each other, right? Repel means they will push each other apart, and in this case, they will be pulled into each other and they'll get joined, right? These will not get joined, they will rather push each other away. So same poles repel, right? I forgot the word poles, right? So one question that I do expect in the paper tomorrow is the ring magnet arrangement. Now this is a very fun experiment. Unfortunately, we don't have these ring magnets in our lab, but just to give you an idea how the ring magnets, if these ring magnets are having a gap, right? If the gap is there, that means they are repelling each other, and it is only possible. Let's just say I give you this question that there's ring magnets, right? They're holding on to each other, just two of them. I'm just making two. I tell you that this pole is north. What is the pole here and what is the pole here, right? What are these poles? So remember, since there is a gap in between them, right? That means, and if this is the north, then obviously this upper part is going to be the south. And if these are repelling each other, if there is a gap, that means this one is a south and the upper one is going to be north, right? So as you can see in this diagram, that north north they're repelling, south south they're repelling, and this Now, more complicated question could be there, right? Just to give an ambiguity, let's say if there's a ring magnet, right? I say this is north and this is upper part is south, right? The upper is south, the lower is north, right? And the second magnet is fully attached to it, right? And the third magnet is floating. So what are the poles on this side and this side, right? And what about this? And what about this one, right? So since these are attracted, as you can say, these are bonded, they're stuck to each other. That means if this was the south, then there must be an opposite pole. So this is going to be north, and this is consequently going to be south, because each magnet has to have two poles. No magnet has a single pole, right? It always has a north and always has a south, right? And again, if these are now having a gap, that means this is now going to be opposite, right? South versus south, and this is now going to be north, right? So I hope this is very understandable to you, that this is a very simple phenomenon of magnetism, right? If you had attended the lab, and if you were focusing on what I was doing in the lab with those magnets, you would be easily able to understand and explain these in your paper, right? Any question you'll be able to easily handle. Now, the question of Earth's magnetic poles, right? Now, I just told you that if, let's say, I have a compass, right? I've got a compass. So, which way is the needle going to point, right? Now, remember, needle of the compass is always north where the pointy side is and south where the back point is, right? And you can easily make your normal magnets very easily. You have seen those experiments. You can read those methods which are available in the book as well. That's why I told you guys to read the book thoroughly, because most of the things would be easily answered if you just read the book once, right? So where is it going to be pointing? It would be pointing towards the top rather than towards the bottom. And why this is not going to work? Reason being that it is going to be, this is north and this is south. Since this is north, it would point towards this, right? And the south will always be focused towards the north, since the opposite poles are to be working together. So if we see that the Earth's magnetic field is there, why the Earth's magnetic field is there? I told you that Earth's magnetic field exist due to the motion of the core. Now, if you remember, that we have a molten core which is spinning, and when it spins, it makes the mantle or the magma, right, to rotate, and that magma is mostly iron plus nickel. When these two metals, which out of which these are magnetic, they create the magnetic field, right, in which there's south on top and north, right? I'm just going to be making arrows, is at the bottom, right? For you guys to have a clear understanding, this is what I've taken a poster from the internet, that if this is the magnetic if this is the core, inner core, and the outer core, which are spinning, they create the magnetic field, and that magnetic field is very strong towards these poles, right? The southern and the northern pole. And remember, the northern pole, or the northern hemisphere is at the bottom, and the southern hemisphere is what is on the top side. So we call these as opposite poles, right? In the naming, when we try to name them, right? Even though the magnetic field is opposite to the geographic pole. Now, what is a geographic pole? Geographic pole is what we call as which side is the top, which side is the bottom. We do know that the Earth's bottom side, top side is the north, and the bottom side is the south, which is the geographic pole. Remember, there's a difference between magnetic pole, right, and geographic pole, right? Geographic pole is what the compass is reading, right? Compass reading. And the magnetic pole is the actual poles which are created by the earth, right? Since our compass is always pointing towards north, which is the top side, I know it makes bit confusion that you've always seen that the north pole is the earth's north is towards where the compass is pointing north. But remember, that is what we call as the geographic pole, which the compass is telling you, while the actual poles are opposite. Otherwise, the compass would be repelled, right? If the compass is attracted towards that point, then it is, your magnetic, it is your geographic pole, right? So keep the difference between the actual magnetic poles and the geographic poles, which the campus is able to read, right? The next point was the formation of electromagnets, right? Now, I'm not going to go into further questions, as you can see, you've seen a few questions in the assessment as well as in the workbook. They're very pretty simple questions related to magnetism and Earth's magnetic field, pretty straightforward descriptive questions. So you just need to read through the book to answer those questions, right? Uh, Now, the more technical questions are coming from this electromagnet. Now, what is an electromagnet? Do you remember this experiment that we did in the lab, right? Picked up a nail, I picked up an insulated wire, right? What this coiled wire is an insulated, I will call it an insulated uh, coil wire, right? Why insulated? Because if it conducts, then this will get shortened out and nothing would be there. So we need an insulator wire, right, which is insulated or covered from the front, so that it does not conduct electricity thoroughly, but only the current goes through the wire and not through the nail, right? If the nail gets electrocuted, then you won't get an electromagnet, right? Because the nail itself has become electrocuted, so there won't be any magnetic field, right? Now, how does this work? When the current goes through this, it forms an magnetic field, and this becomes the north, and this becomes the south pole, right? And this is why it started picking up paper clips. If you remember, we used the paper pins just like this experiment, right? So what are the factors upon which this magnetic field? First, I need to identify what is the difference between a temporary magnet, what we call as an electromagnet, and a permanent magnet, right? A temporary magnet we call as an electromagnet. Reason being, we can simply turn it off. We can take off one wire, and it won't be a magnet anymore. These pins would fall, right? While the permanent magnet can't be switched off, right? We cannot stop its magnetic field. Can't be switched off, right? So that's the problem with permanent magnets, right? That is why we use electromagnets. So one of the applications that I've taken the picture from is the biggest application of electromagnets, which is the scrapyard, right? Where we can separate metal, iron, which needs to be recycled, from all other materials like plastic, right? Because plastic is non-magnetic, so this electromagnetic puller is not going to be able to pull it up. Only iron particles or iron to be recycled, right, will be picked up to be recycled. So this makes our selection very easy. If we start, separating iron from plastic, let's say from cars which are made up of both iron and a lot of plastic parts in it, if we crush them up, right, for these recycling process, we won't be able to separate physically, that easily by hand or by any other process. Electromagnet makes our job easier. When we crush all of that, all the plastic and the metal is now mixed in this form of this scrap, right? Uh, so it makes it very easy for us to separate iron, because iron, being magnetic, will be pulled up by this electromagnet, while the plastic will remain at the bottom or would fall while this is being pulled up, right? So we use these electromagnets. As you can see, this electrical wire is coming over here just to power up this electromagnet. And when we want to drop this into the furnace, we simply turn it off, right? We turn off the electrical power, and all of this iron metal will now fall down, right? So another example is these clocks, right? Battery operated watches that we have, wristwatch, or the wall clocks that we have, which use cells, right? No, those batteries, what they do, they have this tuning fork which moves back and forth. Those arms are there, and they move these gears, which due to the presence of electromagnet, right, electromagnetic movement, the needles will start moving, right? And that is why once the battery is gone, these clocks stop, right? If you remember, I'm using a mechanical watch which does not use a battery, and hence it is different from that. Why I don't like those? Because I have to replace battery, or on and off again, because the batteries get consumed. When the battery is consumed, the clock will stop, your watch will stop working. Hence I prefer a mechanical version, a spring loaded one, rather than these electromagnet. But these are more common. If you want to review this, you can study this whole design. This is like complete detail of how your watch is made. But again, this is out of your course, just giving an idea of where these electromagnets are commonly used. So electromagnets are everywhere, from your cars to your watches, to these scrap yards. I mean, electromagnets got so many applications. If I start listing, I won't be stopping, till the end of the day. Now, investigating electromagnets. So we want to see how to make strong electromagnet, right? So what the electromagnet depends upon, right? What factors? Number one, if you do know that in the lab I had these turns, when I reduced them, less number of pins were reacted, right? So there are two factors. I'm just going to name them: turns of coil, right? These turns, how many turns are there? And number two, amount of current, right? How much current? If I'm giving too much power, then the electromagnet is going to be very strong. If the current is low, uh, the electromagnet is going to be less strong, right? So if I say more current, right? More current. If the current increases, that means stronger magnet, right? Stronger magnetic field will be generated by the electromagnet, right? And number two, if more turns, that will also result in stronger magnetic field, right? So these are the two factors that are there. Now rest of the investigative questions that are there, please understand that those were very easy questions in the assessment. You just needed to look at the number. If you remember, they were like different magnets. We had A electromagnet, B, C, D, and E. Then we had this number 24, 24, and if you read the question properly, if you had read the question properly, it suggested only 24 pens were used, right? Were used. So the student was not able to identify the difference, right? Difference. Why? Because he didn't have more pins. So if he had added more pins, then he would have been able to identify which one was stronger out of the A and B, which in the second experiment, if you know that he was in the diagram, the pins were there, right? The magnet was on top and the pins were there. So if someone's hand is thicker, right, remember, then the magnet, if you remember, if you pull the magnets too far from each other, north and south, right, they are not able to attract. Why they can't attract? Reason being, the more the gap, the less the attraction becomes, and up to a point will come when they're so far away that they are not able to pull on to each other. And this what happened between the first and the second experiment, right? In the second one, if you remember, between A and B, now I'm just going to state A and B, right? He was able to get 24 pins here, but only 18 pins for B, and he was able to identify that B was a weaker magnet and A was stronger. Why? Reason being, he had a thicker hand, so more gap, right? More gap. That made the pins become less, even though he was still using 24 pins. In the first one, you can add more pins, right? Right? That was one method to create a difference, right? And in the second one, the difference was already there, and we were to identify how the difference was there. It was due to the thicker hand, right? Because that is another variable. If you have very thick hand, then the magnetic effect or less number of pins will be lifted up. If you have a thin hand, then the magnet is closer to the pins, hence more number of pins can be attracted, right? This was a very simple question, and I said if you had read the question properly, you would have been able to answer these very very easily, right? It was just out of magnetism. It is just a reading based question. There's nothing calculative in these topics, right? So please be very careful for your final exam. Keep these points, basic points that I've discussed in mind. It's a very simple phenomenon that needs to be discussed, right? I hope you people will be able to answer these questions now in the final paper very very accurately, right? Good luck for your paper. Bye bye.